now it's time for us to do some problems involving parametric curves, seeing what happens as a particle travels through space. Well, really what we're doing is we're starting to understand vector-valued functions and even doing a little bit of calculus. Calculus? What? Yeah, it's true. It's going to be good. So as we start into this new topic, it's important to do problems. Practice. The more you practice, the better you get. So when you see a problem, make use of the pause button. Try it out yourself. And if you do need my help, go ahead and unpause me. And we'll go ahead, we'll figure it out together. Well, let's begin. Our first problem. Find the limit as t goes to 0 of, and then there's this vector valued function, t squared minus 1 e to the t sine t over t. Now, how do you do the limits of vector valued functions? Our mantra is entry by entry. That's almost always going to be the answer. When we say, well, what do we do? How do we handle it? Entry by entry. So for us, we say, look, this is really saying the limit as t goes to 0 of t squared minus 1, the limit as t goes to 0 e to the t, and the limit as t goes to 0 of sine of t over t. All right, great. So now instead of one limit, we have three small limits. That's okay. That's all right. And we're going to see this a lot. So here, t squared minus 1, plug in 0. Easy. E to the t, well, great. Plug in 0 again. 1. Sine t over t, well, you can't plug in 0. I mean, you could, but you get 0 over 0. But sine t over t isn't just any limit. It's a really important one. One that we know the answer to. So sine t over t as t goes to 0 goes to 1. Yes, good. Okay. Now, if you didn't remember it, you could actually do l'hôpital. Oh, but of course, you don't even need to do l'hôpital. It's a very famous limit and an important one underpinning our calculus. But for now, we're done. Good. So again, the mantra, entry by entry, work entry by entry. And at the end of the day, what does it mean? Well, it means we can actually do these problems. It's just going to take us 3 times as long, right? Because we just do it for each entry. There's 3 entries. No problem. No problem. Okay. Well, now let's do another problem. Find all times t where the curve given by, and here we have it as points, but that's perfectly fine. We have t cubed plus e to the t plus 2, minus t plus cosine t plus 1, and 2t plus e to the t plus 2 cosine t. And we want to intersect the plane x plus 2y minus z equals 4. So we have this particle traveling through space, and there's this plane. And the question is, when does it hit the plane? All right, so how do we do it? Well, we just say, look, I want to know when do I hit the plane. The way I do it is I know what x, y, and z are. So I put those in. So for instance, x is t cubed plus e to the t plus 2. All right, and then y minus t plus cosine t plus 1. And z, 2t plus e to the t plus 2 cosine t equals 4. And what have we done here? Well, if you look, we say there's our x plus 2y minus z equals 4. So we've slotted each one in. Great. Now what? Well, time for us to clean it up. Okay, so we'll expand and group, and hopefully nice things will happen. So what do we have? We have t cubed plus e to the t plus 2. Now, don't forget to distribute. So we have minus 2t plus 2 cosine t plus 2. Over here, don't forget the minus sign distributes. Doesn't just go to the first term, goes to all the terms. Minus 2t minus e to the t minus 2 cosine t equals 4. Now, hopefully, things will start to simplify. Because when we start having sort of mixing and matching cosine and exponential and polynomial, it's going to be hard to solve. So maybe some things cancel and becomes a lot easier to work with. Well, for instance, you have an e to the t and a minus e to the t. Cancel. What else do we have? Well, plus 2, that's 4. There's a 4 over there. Cancel. 2 cosine t minus 2 cosine t. Cancel. Minus 2t minus 2t. No, they don't cancel. They combine. Right? They're the same sign. But actually, we're now in a lot better shape. We get t cubed minus 4t equals 0. Everything else cancels out. So, t times t squared minus 4 equals 0. Well, t squared minus 4, a squared minus b squared. A minus b, a plus b. So, wherever they intersect has to be where t times t minus 2 times t plus 2 equals 0. Well, that tells us our solutions are 0, 2, and negative 2. Now, in this case, we were after our times. If we had been after our points, what would we do? Well, if we wanted the points, we would take these numbers and plug them in. So, for instance, if you plug in 0, you get 0 plus 1 plus 2 is 3. Then you have 0 plus 1 plus 1 is 2. And 0 plus 1 plus 2 is 3. So that's 1 point. Of course, these are much more curious. E squared cosine 2. Wow, very, very bizarre numbers. But that's all right. We just needed our times. So we're done. Woohoo! Good. All right. So now we know how to find when do curves hit planes. All right. Well, we should try another problem, right? Of course. We should try as many as we can. The more that we do, the better that we get. We want to be great. So, let's do this problem. Find the tangent line to r of t. So r of t is this vector valued function. E to the 2t minus 3t, sine of 2t minus cosine t, and t squared minus 2t plus 4 at t equals 0. And give your answer in parametric form. Now, if we think about tangent lines, there's actually a really succinct way of writing our tangent lines in vector form. Very, very simple. Because what do we have? Well, whenever we do a line, we always need two things, a point and a slope. So what's our point? Well, our point, we think of in terms of a vector as coming from what happens when we plug our time into our equation. So in this case, it would be r of 0. And our slope, well, that would be r prime of 0. So, whoops, I said point and slope. We're not point and slope. That's single variable. We're point in direction. That's multivariable. Sorry about that. So, r prime of 0, that's the vector that points in the direction we want to go. And if you put them together, that says our line has the form r of 0 plus some multiple t, r prime of 0. Now, I will say this is somewhat bad notation. When we use this t here, that's for the line. It's distinct from the t here, that's for the curve. Unfortunately, it's a notation that gets used a lot, so we have to live with it. Just keep in mind, they are representing different things. So that the t for the curve says that's a parameter for the curve. The t for the line is that's the parameter for the line. Well, let's find the values. So, well, r is 0. Plug in 0. E to the 0 is 1. Minus 0 would leave us with 1. Sine of 0, 0. Cosine of 0 is 1, so we get minus 1. And 0 and 0 and 4. So 1, minus 1, 4. Now to find r prime of 0, a first step would be, what's r prime of t? So we need to take derivatives. And remember, we do it entry by entry, one entry at a time. So r prime of t is, first term, we have what? 2 e to the 2t minus 3, comma. Derivative there, sine of 2t, that's 2 cosine 2t. This 2 comes from the chain rule. Derivative of minus cosine, well, derivative of cosine is negative sign, so since it's being subtracted, minus a negative sign makes it positive sign. Okay. Now, derivative of t squared minus 2t plus 4. That would be 2t minus 2. Good. Now, plug in 0. We'll get 2, because e to 0 is 1, so 2 minus 3 is negative 1. Here, 2 times cosine 0, that's 2, plus 0, so 2. And 2 times 0 minus 2 is minus 2. All right, there we go. Now we have our point and our slope. So in parametric form, because it says, give it in parametric form, we have x equals, y equals, z equals, we put our point in, 1, minus 1, 4, 2, 2, 2, 2, and then our vector for our direction, minus 1t, 2t, minus 2t. So minus 1, 2, minus 2, that's our direction. We can clean up just a little bit. 1 minus t, y equals minus 1 plus 2t, and z equals 4 minus 2t. And we're good. That's it. That's our answer. All right. Wonderful. Okay. Well, let's go on. And let's try another problem. So, let r of t be the vector valued function there. There it is. Find the plane perpendicular to this curve at time t equals 2. Okay, what's going on here? Well, we have some curve going through space. It's doing something. And then we're saying, look, at a particular time, at time t equals 2, the curve is at some point. So it's moving, and there's this point here. And now, what we want is we want to say, well, look, there's some plane that's here where the curve pierces it perpendicularly. All right, so we think to ourselves, all right, what do we need if we need a plane? Now, whenever we need a plane, we need two pieces of information, right? We need a point and a normal vector. So let's think about what that information comes from. Well, how about the point? Well, the point will be this point right here. So the point on our plane will be our vector. So it's going to be what happens at time 2. It's going to be r of 2. How about the normal? Well, what you can think of happening is if you were to zoom in on our picture here, so if we take this part and zoom in, what we'll see is, well, we'll still see the same plane, because if you zoom in on a plane, it looks like a plane. And you zoom in on a flat thing, and it's like, ooh, still flat. Yeah, that's true. But on the other hand, the curve, well, see, originally, it was curvy, but now what happens is it comes through in a nice perpendicular fashion. I'm going to say, okay, so that the tangent line is going to be perpendicular to our plane. Well, okay, so that says the direction of the tangent line is normal, right? Because that's perpendicular. Okay. Well, what's the direction of the tangent line? That's the derivative. So our normal will be r prime of 2. So let's figure this out. R of 2, well, plug in 2. 2 cosine 2 pi. Cosine 2 pi is 1. Okay, so that will just leave us with 2. Sine 2 pi. Sine 2 pi, 0. All right, 2 cubed, 8. All right, so there's our point. Now, our normal. Well, we need to find our derivative, r prime of t. What would that turn out to be? Well, derivative of 2 cosine pi t. Derivative of cosine is negative sine, so it's minus 2 pi sine of pi t. Where did that pi come from? That pi comes from the chain rule, right? Because we got to take the derivative of the inside. All right, well, great. Next entry, derivative of sine of pi t. Well, derivative of sine is cosine. And again, chain rule says multiply by pi in front. Derivative of t cubed, 3t squared. Okay, so plug in 2. Sine of 2 pi, 0. Great. How about the next thing? Cosine 2 pi. Cosine 2 pi is 1. So you get a pi. And 3 times 2 squared, that's 12. All right, now we have our normal, we have our point, we have all our pieces. We just need to put it all together. So we get that our plane is the following. These are our coefficients, 0, pi, 12. The fact that there's a 0 says our plane looks like, well, we'll go ahead and write it like this way, 0x plus pi y plus 12z. Because there is an x term, it's just 0. We'll rewrite it in just a second. Equals something. Well, what's the something? Now that's where our point comes in. So we say, okay, 2 times 0 is 0. Oops, 0. Then we have pi times 0. Pi times 0, right, good. So that's also 0. And then we have 12 times 8. Well, that's 96. So when we plug in our point, we get 0 plus 0 plus 96, which means that's 96. So we'll go ahead and rewrite it without the 0, since oftentimes we don't write zeros into our equations. And there we go. That's it. That's the answer. Woohoo! All right. So now we sort of say, hey, there's this philosophy we see. We can find tangent lines and we can find perpendicular planes. It's the same process, point and vector. So either it's the direction vector of the line or the normal vector to the plane. Good, good. Well, let's try another problem. So here we go. Find the value d so that the plane 2x plus y plus 3z equals d will perpendicularly intersect the curve. R of t is 2t squared plus 8t plus 1, comma, 8t minus 7, comma, t to the fourth minus 8t plus 1. Okay, now, it's kind of like the last problem. See, the last problem says we're going to make a plane that's perpendicular at a particular point. And now we say, well, look, here's a plane. It's perpendicular somewhere, but how do we figure out the right somewhere? And, in some sense, we have to fix the right plane. So, a little different. But now let's sort of think about our philosophy. What do we have? Well, we know that when we think about the direction that the curve goes, the direction is going to be giving the normal to any perpendicular plane. So this is going to be our sort of key we're going to focus on. So what do we have? Well, let's look at r prime. So r prime of t would be 4t plus 8, comma, 8, comma, 4t cubed minus 8. All right, so if I plug in any value for t, that would be the normal for that perpendicular plane, for that given t. Okay, now, you'll notice I told a little white lie there And we're going to see that our little white lie is going to be exposed in just a second. What's the normal to this plane? Well, the normal to that plane is 2, 1, 3, right? So this is the normal we want. And now, at this point, you're going to say, aha, Steve, you're going to not ever succeed because there's no way to make 8 equal to 1. And now, let's go back and talk about the little white lie that we told. We actually told it a couple times. We used the word the normal. But that's not true. When we talk about normals, there's many normals. Because if you have a normal vector, you can always scale it, and that will produce a new normal vector. So, what does that mean? Well, it says, look, I need to have that this vector appropriately scaled becomes that vector, or vice versa. So, we say, aha, here's what we're looking for. We're looking for some combination where 4t plus 8, 8, 4t cubed minus 8 is equal to some scaling factor, I'll use s, 2, 1, 3. In other words, I want them to be parallel. That's what I'm looking for. I need these vectors to be parallel. So wherever they're parallel, that says, okay, that plane has a chance to be perpendicular. Now, we say, okay, well, really, that gives us 3 equations, right? Because we work component by component, entry by entry. So we need 4 times t plus 8 to equal 2 times s, because this s goes through. We need 8 to equal s, because, well, again, it goes through. And 4t cubed minus 8 needs to be 3 times s. Well, we need to solve. I think one of these variables is pretty easy to solve for, and then the other one also won't be so bad. So which one's easy to solve for? Well, it's easy to solve for s. So we see, aha, s equals 8. Well, now let's take that information and plug it in to there. So we get 4 times t plus 8 is equal to 2 times 8, 16. Well, subtract 8, 4 times t equals 8. Divide by 2, divide by 4, t equals 2. Now we should check to make sure that this actually is compatible with the last equation. Okay, so let's see. 4 times 8 minus 8, does that equal 3 times 8? Well, yeah, 32 minus 8 is 24, which is the same as 3 times 8. All right, now, are we done? No. What have we done? Well, what we've now determined is that it's at the time t equals 2 that the direction vector of the line is going to be parallel to the normal vector of the plane we want. So in essence, we found the time that we need this to work. So how do we finish the problem? Well, we know the time. What do we need? To figure out what the value for d is, we really need to find a point. A point would give us what d should be. So we look around and we see, okay, well, since we know our time, we're going to plug this into r of t. So plug, and we're going to do this to get a point. So we're going to get r of 2. So we plug in 2. And what does that turn out to be? Well, 2 times 2 squared, 8, plus 8 times 2, 16, plus 1, comma, then 8 times 2, 16, and minus 7, comma, 2 to the 4th, 16, then minus 16, okay, that's good, plus 1, which is 25. Oh, that's a big number. Oh, that's all right. I mean, it's got to be a number. And 16 minus 7, 9, and 1. Okay, so that's the point that the curve is at time 2. We know the direction is right at time 2. So we say, perfect. We need to have the plane where 2x plus y plus 3z equals d contains that point. So the last thing to do is to say, well, we have that 2 times 25 plus 9 plus 3 times 1 has to equal d. Well, that's 50 plus 9 plus 3. And if you add that up, we end up with 62. And therefore, we need to choose d equals 62 to get that the plane will perpendicularly intersect. And of course, not only do we know that the plane will perpendicularly intersect, we even know the exact point on the curve. We know when it happens. But all we needed was the value for d. And we did that. We found our value. Woohoo! Nice! Nice. Good. We made good progress. Okay, well, keep making progress. We're going to do more problems, right? Yes, of course we will. So, our next problem. Find all lines which are tangent to the parametric curve r of t, t cubed minus 12t plus 3, t squared plus t minus 4, 2t squared plus 5t plus 4, which do not intersect the plane 2x plus 3y minus 3z equals pi. Okay. Well, what does that mean? Well, let's think about sort of the idea. And so if you remember sort of our geometric intuition, we said, look, if you have a plane and you have a line that does not intersect the plane, you might think, well, what does it mean? Well, it really means like somehow like the line is parallel to our plane. So here's our plane, and here's that line. Well, notice that what you can do is you can take the line and you can push it down so that they're sort of like the shadow of the line here in this plane. So that there's this parallel line that sits in the plane. So that there's now one of the lines is completely in the plane and one isn't. What's the point here? Well, remember the point here is that the direction of this line is in the plane. And if our direction is in the plane, well, we know that any direction in the plane is perpendicular to the normal vector. So we say, aha, here's our idea. We need to have that the normal to the plane be perpendicular to our direction. So the direction of our tangent line. All right. That's good. So what do we do? Well, we find these pieces of information and we proceed. Well, what's the normal? What's the normal? The nice thing is you can read off normals. So it's 2, 3, negative 3. Perpendicular. How do you find the direction of a tangent line? We use r prime. Okay, so what is r prime? Well, take the derivative. 3t squared minus 12, comma, 2t plus 1, comma, 4t plus 5. All right, so now we're great. How do we know when two things are perpendicular? The dot product is 0. So 0 is equal to 2, 3, negative 3, dot 3t squared minus 12, 2t plus 1, 4t plus 5. All right, so taking our dot product, multiply 2 times 3t squared minus 12, and that would be 6t squared minus 24, right? That's the first term. 3 times 2t plus 1 would be 6t plus 3. That's the second term. And then negative 3 times 4t plus 5 would be minus 12t minus 15. So negative 3 times 4t plus 5. Well, now we group. We have 6t squared. There's a 6t minus 12t minus 6t. 24, negative 24, plus 3 makes negative 21 minus 15. Well, that's negative 36. Okay, well, lots of 6's there. Let's factor out a 6. 6 times t squared minus 1 t, well, so just minus t, and minus 6. Okay, now does that factor? Well, probably, right? That seems to be what always happens, is that things factor. But in this case, it does factor, right? Because we need two numbers that add together to give us negative 1, multiply to give us negative 6, and we can find two numbers that do that, negative 3, positive 2. So we'll get 6, t minus 3, t plus 2. And you can check. T squared, good, plus 2t minus 3t, minus t, and minus 6. So remember that equals 0. And so we come to the conclusion that it happens at 2 times. And those 2 times are times t equals 3 and negative 2. Now, are we done? No, because what are we looking for? We're not looking for the times, we're looking for the lines. We want to find all the lines. Great. Okay, so if you want to find all the lines, what do we need to do? Well, we need to figure out what happens at each individual one. Well, so let's do t equals 3. Well, our point, we plug 3 in. So 27 minus 36 plus 3. Well, probably it's easier to say, 3 cubed is the 27. 27 plus 3 is 30. And if you subtract 36, you get negative 6. Now, 9 plus 3 is 12 minus 4 is 8. And 18, 2 times 9, plus 15, that's 33, plus 4 makes 37. Okay, well, it's a number, right? Okay, no problem. We don't mind that they're big numbers. R prime of 3. In the grand scheme of things, 37 isn't that big, so, okay, all right. Now, what's next? Well, we need R prime of 3. Well, okay, what is R prime of 3? Well, we have R prime. See, this is R prime. So we plug 3 in. 3 times 9 is 27, and then minus 12. 27 minus 12 would be 15. Okay. Then it'll be 2 times 3 is 6, plus 1, 7. And 4 times 3, 12, plus 5, 17. And so we get x, y, z. We get negative 6, 8, 37. That's our point. Plus 15t, plus 7t, plus 17t. Okay, so that's at 3. Now, we're not done. What else do we need? Well, we need to do at negative 2. Okay, so we repeat the process. Okay, so what do we have? At time t equals negative 2, well, plug in negative 2 into the function. Negative 2 cubed is negative 8. Negative 12 times negative 2 is positive 24, and then plus 3. So really, we have 27, if we combine the last two terms, minus 8 would give us 19 for the first entry, comma. Then it'll be 4 minus 2 minus 4, so that's minus 2, comma. And then here we'll have 8, 2 times negative 2 squared is 8, minus 10 plus 4. Well, that's really like 12 minus 10, which will be positive 2. r prime of negative 2 would be, well, 12 minus 12, 0. And then we have minus 4 plus 1, minus 3. And then here we'd have minus 8 plus 5, minus 3 again. That's perfectly fine. And so what do we get? X, Y, Z, 19, negative 2, 2. So we put in our point. Then 0t, well, we don't need to write anything, minus 3t, minus 3t. And there we go. There we go. That's it. And these are all of the lines. There's two of them, which are tangent to the parametric curve, and they don't intersect the plane. Now, you might say, technically, don't we have to do one more thing? It's possible that what we've done is we've actually found a line that's in the plane, which definitely would intersect. But that's not going to be the case because pi is such a weird number. See, when you plug in these points, negative 8, 37, negative 6, 8, 37, or 19, negative 2, 2, into the right-hand side, there's no way you're going to get pi out. So they're definitely not in the plane. So we're done. Woohoo! Nice. What a fun problem. What a fun problem. Okay. Well, which means we should do more fun problems. So our next one. The curve r of t, which is t squared minus 2t, and t to the fourth minus 4t squared, and t cubed minus 3t squared plus 2t, has intersecting tangent lines at times t equals 0 and t equals 2. So find cosine of theta, where theta is the angle between these two tangent lines. So what's our picture? Well, the idea is we're in our three-dimensional space, and we have these curves which are somehow moving around, and it crosses itself. In other words, at a particular set of times, at times t equals 0 and t equals 2, it's at the same location. So I've looped back around and crossed over myself again. We can even figure out what that point is. If you plug it in, at time 0, you get 0, 0, 0. So, I should have happened at the origin. Oh well, just a picture for intuition, right? And if you plug in 2, you'll get 4 minus 4 is 0, 16 minus 16 is 0, and here you get 8 minus 12 plus 4 is 0. So they cross through the origin. Now, what do we want to do? Well, the idea here, the intuition says, look close. And so, if we were to zoom in, what we would see is the following picture. That we have this point here of intersection, and then what we see is that the curve, because we've zoomed in really close, it looks like just two lines that are crossing through each other. So our goal is to find this angle here, the angle between them. Well, not the angle actually. What do we want? The cosine of the angle. Well, how do we find that? Well, whenever you see a cosine theta, your mind should start saying, whoa, we saw cosine theta somewhere before. And dot is something we should remember. It's the dot product. So we have cosine of theta is u dot v over magnitude of u, magnitude of v, where u and v are vectors. So the question becomes, what are the right u and v? Because once we have that, then we just plug it in and life is good. Well, the direction vectors for the tangent lines are the ones that we should be using. So we say, okay, so there are the u and v are the direction vectors. So now we have our idea. We're going to let u be r prime at 0 and v be r prime at 2. And then once we have these, we plug it in. So let's figure out what is r prime. R prime of t, well, take it entry by entry. So 2, 4t minus 2, comma, 4t cubed minus 16t, comma. Then it'll be 3t squared minus 6t plus 2. Okay, so we went through every term, took the derivative every single slot. Now, what comes next? Well, the next thing is to say, whoops, we made a mistake here. Derivative of t to the fourth is 4t cubed. Derivative of minus 4t squared is minus 8t. Now, ideally, you should not always make mistakes to try to catch them later. But it's good to double check, because unfortunately, there's not really a lot of how do you check your work at the end. You don't really have a mechanism in place. So it's really useful to make sure, okay, constantly double check, scan and say, whoops, did I do it right? Oh, whoops, I made a mistake. And that's okay. Like, haha, I'm glad I caught it early this time instead of catching it late, or even worse, never catching it at all. So, r prime of 0. Well, plug it in. Minus 2, comma, 0. Nice. Comma, 0, 0, 2. Okay, well, that's going to be nice. We got a 0. We're always happy to get 0 involved. Of course, if they'd all been 0, we'd be panicking a little bit, but that's not the case. R prime of 2, 4 minus 2, positive 2. And here, ooh, okay, 2 cubed is 8 times 4 makes it 32. 8 times 2 is 16. 32 minus 16 is positive 16. Now, 12 minus 12 plus 2 is 2. All right, and there we go. There we go. So, we're almost there. So, here we go. We know our answer is going to be cosine of theta is minus 2, 0, 2 dot 2, 16, 2 divide by the magnitudes minus 2, 0, 2 and the magnitude of 2, 16, 2. Well, if we do our dot product upstairs, minus 2 times 2, minus 4, 0 times 16, 0, and 2 times 2, 4. All right, divide by downstairs, well, the square root of 4 plus 4. And there's another 0 I didn't put in there. Square root of 4 plus 256, which is 16 squared plus 4. Now, the good news is we can see something lovely has happened upstairs. Minus 4 plus 0 plus 4 is 0, which means it doesn't really matter downstairs. We got cosine of theta is 0. Wow, amazing, amazing. Well, what does that really tell us? Well, what it tells us is that they actually are perpendicular. So our picture, it was kind of, looked like they were perpendicular in our picture. Of course, it may have been actually like that, but in this case, it worked out. Wow, cool, beautiful, beautiful. Who knew? Well, we did once we did the work. But, you always have to do the work. That's the important thing. Okay, well, good, good. So let's do one more problem. While holding an egg, you travel along this curve into something. Now notice that this is presented in a slightly different format, where instead of having it as, a list of entries, we have something times I, something times j, something times k. You can do either one. They both represent the same thing. We shouldn't let notation prevent us from making progress. We shouldn't say, well, it's a different notation. I guess I can't do anything. And either one, you adapt to the new notation, or you say, well, let me just jump back to the one I'm familiar with. So we could have written this, by the way, in the t cubed plus t, comma, 6t squared minus 7, comma, 7 minus t cubed form. It's the same thing. All right, at time t equals 1, you let go of the egg. Okay, so we're traveling with this egg, and we release. Now, what happens? Well, the egg isn't going to follow you because you're moving along the curve, but you're no longer holding onto the egg. So the egg doesn't somehow magically follow along. That's not what eggs do. Eggs aren't magical in that sense. Well, so what does it do? Well, it continues in some straight line. Now, the question is what's going to happen? In particular, where will the egg hit the xy plane? So, what's our picture here? Well, we have here the xy plane. So here's our xy plane. And we move along in some curve. So there's our curve on which we travel. And at a particular time, we release. So maybe this is where we're at time t equals 1. And what will happen is that it'll continue in a straight line until we hit. Now, once you hit the xy plane, of course, then you're going to have a bit of a yolky mess. It's going to break open, but that's okay. We don't mind. That's not really part of our problem. We don't have to, somehow reassemble our egg. That's we'll leave that for other people to do. Okay, so now, of course, the question is, where does it hit the xy plane? To answer that, we need to think about, well, what's this line it's following? Now, if you think about it, the egg isn't going to be released because we're releasing. We're not like chucking it. We're just like doop, letting it go. It's not going to fly off in some sort of sporadic direction. What it'll do is it will follow the current motion. So we say, okay, here's the key idea. This line is our tangent line. And so that's our key idea, is we need the tangent line at time t equals 1. And then, once we have that, we move on from there. Okay, so here we go. We start, say, all right, if we need our tangent line at time t equals 1, so we're going to have to find our point and our slope. So our point is going to be r of 1. So we plug in 1. 1 plus 1 is 2. 6 minus 1, negative 1. 7 minus 1 is 6. Now, our vector, our direction vector, if you will, r prime of 1. Well, better do r prime. R prime of t is 3t squared plus 1, comma, 12t, comma, minus 3t squared. So when we plug in 1, we'll get 4, comma, 12, comma, negative 3. All right. So here we go. Now, our tangent line is x equals y equals z equals our point, 2 minus 1, 6. Our vector, 4t, 12t, minus 3t. Okay, so there's our tangent line. I want to pause for a second here and be careful to say the t here on that curve does not match with the t there on the tangent line. They are different t's, and I know that's bad form, but people are so used to saying, well, t represents our parameterization, our time, so that's what we're going to use, and we're just going to have to live with it. That's the tradition. Okay, all right. Other than our bad notation, now we're in great shape. So we think about, well, we want to know where we hit the xy plane. And we say to ourselves, how do we know we're on the xy plane? Well, that would be true when z equals 0. Okay, so we come here to our line and say, when does the z part equals 0. That's not so bad to solve for. We can rearrange. That tells us here that t needs to equal 2. Okay, well, now that we know what t is, plug it in for x and for y. And what do we get? 2 plus 4 times 2. Well, that's 2 plus 8, which is 10, comma. Negative 1 plus 12 times 2. Negative 1 plus 24. That's 23. And comma, 0. And therefore, that's our point. 10, 23, 0. That's where we're going to have our egg hit the xy plane. All right. Great. Well, a lot of good practice. Of course, the more practice you do, the better you get. So keep at it. Keep doing the practice, and we'll see you again at another session.